Over 1 billion young adults right now are at risk of permanently losing their hearing, yet scientists are closer than ever to a biological cure. Today, we will dive into the hidden epidemic of hearing loss, explain how to easily bulletproof your ears, and explore the futuristic biotechnology that might just reverse deafness for good, according to recent data from the National Health and Nutrition Examination Survey and the National Health and Aging Trend Study. Approximately 22.2% of the overall United States population suffers from hearing loss. This prevalence seems to strongly correlate with age. While 11.24% of children and 14% of younger adults experience auditory deficits, the rate sharply accelerates later in life. By age 71, 65.3% of individuals are affected, and for those 90 and older, hearing loss is nearly universal at 96.2%. The dominant driver after age 60 is presbycusis, which is age-related hearing loss caused by cumulative oxidative stress and ongoing inner ear degeneration. For younger populations, noise-induced hearing loss acts as the leading preventable driver when compared across all age groups. There are also secondary drivers compounding this damage, including cardiovascular and metabolic comorbidities, genetic susceptibility, and ototoxic medications like certain chemotherapy drugs. To understand how these various drivers destroy our hearing, we must first distinguish between the two fundamental ways the ear can fail. Why do some hearing problems vanish with a simple medical procedure while others require lifelong management? The answer lies in the structural differences between conductive and sensorineural hearing loss. Conductive hearing loss occurs when physical barriers in the outer or middle ear block sound waves. According to the American Academy of Audiology, these blockages typically stem from earwax impaction, middle ear fluid, or ossicular bone fixation, a condition where the small bones in your middle ear become stuck together, preventing them from vibrating properly. This leads to lower incoming sound volume without distorting the audio quality. Because the inner ear remains intact, medical interventions often reverse this loss completely. On an audiogram, this manifests as an air-bone gap. Bone conduction thresholds measure normal, while air conduction thresholds read abnormally high. Conversely, sensorineural hearing loss, or SNHL, involves cellular or neural degradation. Data from the National Institutes of Health shows SNHL accounts for approximately 90% of all cases worldwide. Damage localizes to the cochlear hair cells or the auditory nerve itself. Unlike conductive loss, SNHL reduces volume while introducing severe distortion, specifically degrading high-frequency sounds. Because human cochlear hair cells do not regenerate, SNHL is typically permanent. Audiometric testing confirms when air and bone conduction thresholds are equally elevated, proving the sound signal fails at the sensory processing stage rather than the transmission stage. The most common and preventable form of this permanent sensory damage is driven entirely by the loud environments we voluntarily expose ourselves to. Why does prolonged exposure to loud noise permanently erase hearing? According to World Health Organization guidelines, this happens when exposure to sounds exceeding 85 decibels, roughly the volume of heavy traffic. The process begins with mechanical trauma. Intense sound waves generate excessive shearing forces that physically damage the basilar membrane and bend the stereocilia, the sensory hair cells inside the cochlea. This mechanical stress drives an immediate metabolic overload. Studies published in the Journal of Audiology demonstrate that this stress triggers a high level of glutamate release and generates reactive oxygen species. The resulting oxidative stress and calcium overload from the glutamate release cause sterile inflammation, ultimately forcing apoptosis or programmed cell death of the sensory cells. Because human hair cells do not naturally regenerate, this cellular death is permanent. The resulting threshold shift frequently appears first as a high-frequency notch on clinical audiograms. While this cellular death has historically been permanent, modern science is developing ways to repair the ear at the genetic level. How do we treat sensorineural hearing loss rather than just amplify sound? Biotechnology is shifting from palliative devices like hearing aids toward biological interventions. 3 innovations lead this space: AAV-based gene therapy, otic neural progenitor cell therapy, and pharmacological hair cell regeneration. I'll explain what each of these do. The first innovation, adeno-associated virus-based gene therapy, is demonstrated by Regeneron's Decibel Otofillin, or DBOTO program. The Decibel Otofillin program uses a modified viral vector to deliver a functional OTOF gene directly to the cochlea. This mechanism restores otofillin protein expression inside inner hair cells, allowing them to translate sound vibrations into neural signals. The overarching ambition is a single-dose treatment, restoring natural acoustic hearing for genetic sensorineural hearing loss. Evidence of this mechanism's viability appears in Regeneron's Phase 1 TAF cord trial data. 11 of 12 profoundly deaf children experienced clinically meaningful auditory improvements, and 3 achieved normal hearing sensitivity. Beyond inserting healthy genes, researchers are now learning how to physically rebuild the broken neural pathways inside the inner ear. While cochlear implants merely bypass a failing ear, what if we could physically rebuild the damaged auditory nerve? The second major biotechnology innovation aims to do exactly that using otic neural progenitor cell therapy. Rinri Therapeutics currently leads this application with their RINCell-1 program. The mechanism requires a precise, step-by-step biological intervention. First, surgeons transplant allogeneic stem cell-derived neural progenitors directly into the cochlea. Once delivered, these progenitor cells are intended to differentiate and physically regenerate damaged auditory nerve fibers. Finally, these new fibers attempt to rebuild the vital synapses connecting the inner ear to the brain. The objective is strict disease modification, rather than managing progressive decline with hardware. Researchers intend to reverse adult neural sensorineural hearing loss, specifically targeting age-related sensorineural hearing loss. Regulatory progress is moving forward based on concrete data. According to clinical trial registries, the UK MHRA approved a Phase 1/2, a first-in-human trial for RINCell-1 in July 2025. This specific trial targets 20 adults who are currently eligible for cochlear implants. We could expect definitive proof of concept data regarding safety and cellular engraftment to be published between 2026 and 2027. While cell transplants offer a surgical solution, the ultimate holy grail of audiology is a simple pill that forces the ear to heal itself. Allow me to explain. The third major innovation in this space is pharmacological hair cell regeneration. Instead of invasive implants, this approach aims to restore hearing through oral or injectable small molecule drugs. The mechanism targets adult non-sensory supporting cells located inside the cochlea. By exposing these dormant cells to specific small molecules, researchers aim to reprogram them, triggering a structural conversion into fully functional sensory hair cells. The overarching ambition is to deliver a highly scalable, non-invasive pharmaceutical treatment for adults with irreversible sensorineural hearing loss, or SNHL, caused by noise, aging, or ototoxicity. Progress is advancing rapidly. In December 2025, Shionogi and Salubritas Therapeutics entered a joint research and development agreement. This partnership aims to translate Harvard-led preclinical proof-of-concept studies into human clinical trials, testing the safety and efficacy of these compounds in live patients. While these cutting-edge biological cures work their way through clinical trials, you must rely on behavioral strategies to preserve your hearing right now. Here's how. To prevent noise-induced hearing loss before requiring medical intervention, you can rely on 2 primary behavioral strategies to mitigate risk. The first strategy is the 60-60 rule for personal audio devices. This protocol restricts listening to no more than 60% of maximum volume for a maximum of 60 continuous minutes, followed by a mandatory quiet break. The mechanism relies on cellular recovery. High decibel sound forces cochlear hair cells into metabolic overdrive. Limiting intensity and duration prevents structural exhaustion, giving the auditory system time to clear oxidative stress. The scale of auditory risk is quite massive. The World Health Organization estimates that 1.1 billion young people globally risk hearing loss from unsafe recreational listening practices. A 2025 study of medical students substantiated this claim, finding that individuals routinely violating the 60-60 rule with portable media players experience significantly higher rates of tinnitus, which is when you perceive sound when no external noise is present, and auditory fatigue. Unchecked acoustic trauma can also provoke sudden sensorineural failure. In one extreme clinical case, a young DJ consistently monitored live music at maximum volume. Mid-set, one ear went completely silent, ultimately resulting in permanent asymmetric hearing loss and chronic tinnitus. Controlling your headphone volume is easy, but you also need a proven defense mechanism for when you step out into loud public environments. The second primary strategy you could adopt to prevent noise-induced hearing loss is to use of high-fidelity earplugs in loud recreational environments, like a DJ concert I mentioned earlier. Standard foam earplugs won't block all noise frequencies efficiently compared to high-fidelity ones that utilize specialized acoustic filters. These filters attenuate all sound frequencies evenly, reducing overall noise exposure by 15 to 20 decibels. This protects delicate cochlear hair cells from mechanical overload while precisely preserving musical clarity. Clinical evidence strongly supports this intervention. A 2016 randomized clinical trial by Ramakers et al. Demonstrated that festival attendees wearing earplugs experienced significantly fewer temporary threshold shifts and reduced post-event tinnitus compared to unprotected subjects. Despite these documented clinical benefits, Centers for Disease Control surveys indicate only about 8% of US adults consistently utilize hearing protection at loud events. The adverse outcomes of unprotected exposure are well documented. A 2024 survey detailed a 15-year-old patient who developed severe chronic tinnitus following a single unprotected concert. The patient characterized the persistent ringing as replicating the exact volume of standing adjacent to a busy motorway. Protecting your ears from immediate trauma is the single best investment you can make for your long-term auditory health. And now you understand why. Hearing loss is a widespread, cumulative, and largely irreversible condition that deeply impacts your daily quality of life. But it absolutely does not have to be your inevitable fate. By taking immediate action with simple, proven habits like the 60-60 rule and keeping high-fidelity earplugs on hand, you can protect your delicate inner ear cells today. Meanwhile, an inspiring wave of biotech breakthroughs ranging from gene and cell therapies to regenerative drugs offers concrete promise that biological cures for deafness are rapidly approaching reality. Take care of your ears now, and science might just take care of the rest.